Hi guys, Mr. J here. Today we're going to talk about what's called VSEPR theory. VSEPR theory tells us the shape of these molecules that we have been looking at. What shape do they take in a three-dimensional space, or what is their molecular geometry? Once we know their molecular geometry, we can make some inferences about some of their properties, which is why we're learning about it. This is what I told you at the beginning of the year. We're going to save this towards the end because it's not super hard, but there is a lot of memorization on it. So you will have to put in some effort to memorize the different shapes, but it's not too bad. So go ahead and follow along with me. VSEPR stands for valence shell electron pair repulsion theory. That's a mouthful, so we just call it the VSEPR theory. In VSEPR theory, the heart of it is being able to draw those Lewis structures that we talked about, I think, in our last video. So remember, the Lewis electron pair approach, it predicts the number and types of bonds between atoms. We used the valence electrons to draw those Lewis structure diagrams. And it indicates if do we have just bonds between atoms, or is there some bonded pair electrons and also what we call the lone pair electrons that aren't attached to anybody, okay? But they don't give any information about the actual arrangement of the atom space. It doesn't tell us what their three-dimensional shape looks like, and that's where the VSEPR theory comes in, okay? It's going to predict the shape of the molecules and polyatomic molecules based on those bonded pair of electrons and the lone pair of electrons. Those will determine the shape of it. Okay, so as I said earlier, the name tells you the story. Valence shell, well, that refers to electrons that are found on the outside, the s and p orbitals. Okay, electron pair repulsion, well, what we see with this is that the electrons try to get as far away from each other as possible. Remember, electrons are negative, like charges repel, so they want to maximize the distance between them. And the way we kind of quantify that is looking at the angles between the different atoms. Okay, what angle do they have to get at to maximize that repulsion theory? Okay, and basically the structure of a molecule then is given around an atom. It's determined by minimizing that electron pair repulsion. What's the closest we can get them together and get a shape is where that comes out of. Okay, and as we said earlier, it's based on the number of bonded pair and then the number of unbonded electrons. We call these domains that are around us given atom. Okay, and as I said, the electron pairs want to orient themselves in order to minimize these repulsive forces. They want to get as far apart as they possibly can. Okay, so when we talk about VSEPR theory, first we need to identify types of electrons. Okay, there's two types that we're going to be interested in. The first is what we call a bonded pair. Okay, and these are electrons that form bonds, so we can see them down here. We represent them as just straight lines. Okay, they're sharing those electrons. The other electrons we call lone pairs. Okay, and those we just have when our Lewis structures are represented by the different dots here. Okay, so we have bonding pairs, those forms a bond, and then the lone pairs are the electrons that we find on the outside of them. Here's looking at another one. Here's chlorine, right? They're sharing this one, so we get a bonded pair here, and then on the electrons on the outside are our lone pairs. So we got to keep those two in mind as we go through this. Okay, so the VSEPR theory, as we said, electron pairs repel each other. Okay, they try to remain far apart from each other as possible. Okay, and what we see when we compare the repelling of the lone pairs compared to the bonded pairs, the lone pairs repel more strongly than the bonded pairs. So if we look at something like this, where we have four different atoms around a central atom, we'd expect to be about 109-degree angle between them. Now, if we replace one of these hydrogen with a lone pair, well, that lone pair has more ability to push those angles. So what we see is the angles between these hydrogens down here actually become smaller than 109. Now, if we replace another hydrogen here with another lone pair, we actually even decrease that more. And you can see the same thing over here. So as we add more lone pairs, the angles between the other elements decrease. Okay, so the angle between the other elements are less than we would be expected. So keep that in mind when we come back to it a little bit later. Okay, so what we see is that when we do VSEPR theories, we're going to arrange these atoms around a central atom, and it depends on the pairs of bonded electrons, and the number of lone pairs. And what we're looking is what we call the steric number, which is also known as domain. Steric number or domains is how many things are attached to that central atom, and that includes lone pairs. Okay, so two atoms in a lone pair count as one lone pair, and a bond count as one. Okay, so the position of atoms in space or its molecular geometry is determined by the relative position of the electron pairs. Okay, that the position they take after we take into account the repulsion. Okay, the fact that like charges don't want to be put together is what we're looking at. So let's talk about how we figure out the shape. Well, the first thing, as we said, we got to be able to draw the Lewis structure for the molecule, because that's going to determine our number of bonding pairs and also our number of lone pairs. Okay, and then what we're going to do is we're going to count the number of domains, or the number of things around a central atom. And a bonded pair and a lone pair both count as one. Okay, the difference comes in that the lone pair is going to distort the angle a little more than a bonded pair will. Okay, and then the third thing is need to do is determine the position of atoms. Okay, from the way the electron pairs are shared. Okay, are they shared, like I said, as a bonded pair, or are they a lone pair? Okay, and so the shape is determined by the number of bonding pairs or lone pairs. Okay, and then finally we're going to determine the name of the molecular structure from positions of atoms. This is where the memorization part comes in, which makes it a little difficult. All right, there are 5 basic arrangements about a central atom. The first one is what we call linear. Okay, linear takes on the form of AB2, where A is your central atom and B is the number of bonded atoms towards it. Okay, so we would say this has 2 domains, because here's our central atom. We have 2 things bonded to it. So this is going to, linear means a straight line. So if there's no lone pairs, we're going to expect 180 degrees. Our second type is what we call trigonal planar, where it's AB3 is our generic formula. A is our central atom again. B, we have 3 things around it, so we're going to have 3 domains. Okay, and we call that trigonal planar, where if we take 360 degrees, divide them each, we expect to be 120 degrees if there are no lone pairs. Our fourth one is tetrahedral. Or I guess our third one, excuse me, it's AB4, so we have 4 domains on there, and this is a tetrahedral shape. Now we're going from flat to a pyramidal shape. We've kind of gone 3-dimensional now. And what we see is we're looking about 109 degree bond angles. You're asking, do I need to know these? The answer is, unfortunately, yes. AP will ask you questions about them. So you do need to know those bond angles. And then we have our next one, trigonal bipyramidal, AB5. Once again, we're going to have 5 domains around that central atom, something like this. And we get 2 different bond angles. We get 120 and a 90 degree, depending where they are in space, and we'll get to that a little more. And finally, the last one we call octahedral. AB6 is our generic formula. So we have 6 domains there, and it looks something like this. And in this case, all the angles are 90 degrees. Okay, so let's get into looking at these in a little more details. And so here's just looking at different arrangements. Here's our linear straight line, our trigonal planar. Once again, it's only basically 2-dimensional. Once we got the tetrahedral here, now we've added that whole 3rd dimensional, so it looks like a pyramid there. Trigonal bipyramidal. We got a top and a bottom to it, so we got 90 degrees this way. Okay, but then we also, if we're talking up and down, there's 90 degrees, but if we look at it from the top, we have 120 between this atom and this atom. And then finally, with octahedral, everybody is at a 90 degrees. Okay. Now, everything we've talked about so far does assume that there's no lone pairs. Now, lone pairs are going to shift these angles. They're going to decrease the angles between the atoms because, as we said, the lone pairs have a tendency to repel more than the bonded pairs. All right, so let's look at some of these, go through these really quick. Our first one we said is linear. And beryllium hydride is an example of that. If we pause this really quick and draw the Lewis structure for this one. See if you can do it real quick. All right, hopefully you got something that looks like this. Okay, so what we see is we don't have any lone pairs on this, so nice and easy. Okay, so if we look at, we have 2 domains total, meaning attached to beryllium, there's one here and one there. 2 domains. We have 2 bonded pairs and 0 lone pairs. So we call this a linear structure. The bond angles are 180. We can draw it out looking something like that. Okay, our next one then was trigonal planar. Okay, BF3, go ahead and pause this. Draw your Lewis structure. You can never get enough practice on that. I'll wait. Done? Or are you cheating? Stop. Draw it. All right, BF3 comes something like this. Once again, first thing we notice is attached to the B, there's 1, 2, 3 things. So it's 3 domains. There are no Lewis dots. There's no dots here. No, the boron does not have it only has 6 electrons. It doesn't have the full 8 because we ran out of electrons. Okay, so 3 domains, 3 bonded pairs, 0 lone pairs. So if we were to take this, right, a circle here, 360, divided by 3, we should get 120 degree for our angles. So it looks like this. It's 2-dimensional still. It hasn't gone up to the 3-dimensional. Okay, our next one then is tetrahedral. And CH4 methane, go ahead and draw this one and come back. Okay, when we do methane, okay, we actually now, while it looks here like it's kind of a 2-dimensional, it's actually going to be a 3-dimensional shape. On the carbon, we have 1, 2, 3, 4 domains. Carbon has all its electrons, so it has no lone pairs. Okay, so we would expect it, when we look at our 3-dimensional shape, it's about 109.5. It's not the 90 degrees here, because now we've gone from flat, now we're into a 3-dimensional shape, and that's just something you're going to have to memorize. Okay, so this is what our 3-dimensional shape looks like. It's not flat, but in that kind of that pyramid type shape. Or there's another better way of looking at it there as well. Our next one then was trigonal bipyramidal, PCl5. This one's a little weird because we have an expanded octet, which means that around phosphorus is 2, 4, 6, 8, 10 electrons. Okay, but if you draw them all, you can figure this out pretty easy. All right, so now we have 5 domains around there, no lone pairs. Okay, and it's going to be 120 degrees if we look on the flat part this way, and then 90 degrees if we look this way. So I'll show you a picture of what that looks like. So once again, here's our 90 degrees up and to the side, and then looking at the flat part, the planar part, we got 120 degrees between each of these. Another way to represent it. And then finally, our last one is an octahedral. Sulfur hexafluoride. That's the stuff that makes you sound like Darth Vader, lowers your voices. Okay, there's our Lewis structure for that. Once again, an expanded octet. We have 6 domains around sulfur. Okay, no lone pairs. Okay, so we get a 90-degree bond angle on there. So here's a good example. There's 90 degrees this way, and then 90 degrees this way as well. Okay, guys, unfortunately, yes, these are things that you're just going to have to memorize these based off of the Lewis structure. So make sure you can A, draw Lewis structures, and B, start memorizing these. All right, as we said earlier, when we have lone pairs in, they're going to affect these angles between our attached atoms more than just a bonded pair. Everything we've done so far did not have lone pairs, so we were able to basically take the number of pairs and the angle they were and divide to get the answer. But what we see now is that these lone pairs, because they repulse more than the bonds, they are going to reduce the angle between here, okay? So we reduce this bond angle, and this is where it gets a little more memorization to it, okay? So if we look at this one, here's CH4, okay? Right, tetrahedral shape, we said it's 109 degrees between all these. Now, if we do NH3 ammonia, we got a lone pair here. So look what happens down here. The bond between these hydrogens now went from 109 to 107 because this is repulsing more. Now if we do H2O, water, we have 2 lone pairs here. So we're going to reduce that bond angle even more to 104.5. Okay, so this is where it gets a little bit tricky, and like I said, unfortunately, yes, AP often asks you about these bond angles. Okay, so let's look at some variations of what we just talked about. If we have 4 atoms bonded or 4 domains, we said that was a tetrahedron. We should expect 109.5 degrees. Okay, but it's a pyramid with a triangular base. It takes it from basically 2 dimensions up to 3 dimensions here. Okay, and it's a shape for everything with 4 pairs. Now that's our basic shape. What we then talk about is what happens when we get the lone pairs going. So if we have 4 domains still, but we have 3 bonded pairs and 1 lone pair like ammonia we just looked at, we said this is going to reduce this bond angle to less than 109.5. I think it was 107 actually. Okay, it's still a tetrahedral shape overall. Okay, but we can't see this electron pair. It's not bonded to anybody. Okay, so the shape now is called trigonal pyramidal. Okay, trigonal because we got 3 here, but it's actually a pyramid. And I'm going to give you a chart on all this stuff to help you through it. Okay, now let's go to water. Still, we have 4 things bonded to the water. There's 1, 2, 3, 4, but 2 of them are lone pairs, so we're going to get even more reduced between that. We had 109, then we went to 107. This is probably going to be about 104 degrees in there. Okay, it's still tetrahedral. Okay, but now we can't see 2 of these things, 2 of these domains. So what we end up calling this is a bent shape. Okay, think of it as being bent this way. So if we look at 3 domains, the basic shape, remember, was trigonal planar. We also got this when we had 4 domains, and one of those was a lone pair. Okay, if we have 2 bonded pairs and 1 lone pair, what we're going to call it, its arrangement is still trigonal planar, but the shape is going to be a bent shape here because we have this one up here that we don't see, but it affects it. Like I said, I'll give you a chart with all these on. Going back to our 4 domains we just talked about, remember our basic shape is tetrahedral with 1 pair. Okay, we call it trigonal planar. We don't have that upper pair. It's kind of hidden. We don't see it because it's just electrons, so we got the trigonal. And then if we have 2 lone pairs, we call that a bent shape. Okay, it kind of looks linear because you're going to have 3 atoms like this, but it's going to be a bent shape. Sorry if that came out weird. Now if we have 5 domains, remember our basic 5 was a trigonal bipyramidal, which means we have a point up top and a point down bottom. Okay. If we have 1 lone pair, we call this a seesaw. If we have 2 lone pairs, we call it a T-shape. And if we have 3 lone pairs, we call it linear. Okay, trust me, I will give you a sheet to help you on this. And then finally 6, remember it's octahedral. If we have 1 lone pair, it's called a square pyramidal. If we have 2 lone pairs, it's called a square planar. Okay. All right, keep going. So here's our linear shape. Basic linear shape, straight line. There's our trigonal planar. Okay, here is a bent shape. Okay, with 1 lone pair. Okay, here's our tetrahedral. Now if we replace one of those, we get now basically our trigonal planar. And then if we replace 2 of them, once again, we're going to get a bent there. We can go now to with our 5 domains, right? We have a trigonal bipyramidal, and then we start putting in lone pairs. We end up with what's called a regular tetrahedral, also known as a seesaw. Okay, if we have 2 lone pairs, we get the T shape. You can see it there really well. Okay, and if we put 3 lone pairs, once again, look, it's a straight line, so it's going to be linear. Okay, like I said, a lot to memorize in these. And then here's our 6, right? 6 is octahedral. Okay, if we put in 1 lone pair, we call it a square pyramidal. If we put in 2 lone pairs, we get a square planar because it's a square basically on 1 plane. And so here's one of the cheat sheets, guys. I'm going to give you something very similar to this, but what you'll look at is how many shared pairs of electrons, how many unshared. The ideal geometry means, well, what's our domain? It's based off of the number of domains we have. Now, our observed then is what is the effect of these unshared pairs on it. So that's what we're looking at on this. Okay, let's do a couple practice problems. Determine the shape, include the bond angles for SiCl4. So you should pause this video real quick and go ahead and write the Lewis structure and see if you can figure this out. Okay, there's our Lewis structure for it. So let's see, we got no lone pairs. We got 1, 2, 3, 4 domains. So now we're going to go up in that kind of three-dimensional. Okay, so 4 bonded, 0 lone pairs. There's our generic formula for it. And it's going to be a tetrahedral. So we're going up to that kind of pyramidal shape. I was trying to see if I have a pyramid here. I don't. All right, let's try another one. And there's here's what it would look like in 3 dimensionals. Try this one. I know we did the 03. We used this as a demo in our podcast on Lewis structure. So see if you can remember how to draw this one out. Pause it. Just as a little side note here, right? We can have some resonance going on here. So look here. We have 1, 2, 3 domains total. But we have 2 bonded pairs and 1 lone pair. So 3 domain, that'd be a trigonal planar. And then 2 bonded and 1 pair. Well, this is going to be? This is our basic shape, which is going to be bent. Okay? And so it's about 120. It's actually probably a little less than 120 because the repulsion force of that. So if you wrote, that's your bond angles less than 120, it'd probably be a good answer. Okay, so there is what our domains, but we never see this top one, so we get this nice bend shape here. And look at ozone. So yeah, like I said, it's a little less than 116 because of this lone pair pushing it off a little bit farther. Okay, how about the H2O? Try to draw this one. Now this one you should be able to do pretty easy. There's it. Okay, so once again, how many domains? 1, 2, 3, 4. 2 bonds, 2 lone pairs. Okay, so it's definitely going to shape it. It should be tetrahedral because there's 4 domains, but we're going to shape it into basically 3 elements, right? Which would be linear, but then we got the repulsion theories on. So once again, like the previous one, this is going to be bent, and we're looking about 104 degrees on there, looking something like this. There's another book in water. Okay, another one here. Determine the shape for ammonia, NH3. I think we saw this one earlier, but see if you can draw the Lewis structure for this again and determine the bond angles and the name for it. Okay, so 4 domains once again, hey, just like water, but we have 3 bonded pairs in 1 lone pair. So we were at tetrahedral, right? Should be tetrahedral, but we don't end up seeing, sorry, touch screen there. We don't see this lone pair, so now it comes down to 3 bonded 1 pair, so trigonal pyramidal at about 107 degrees. Remember, we said normally 109 degrees, but because of that repulsion of the lone pair, it's going to decrease that as well. Another look at it there. Okay, guys, this is similar to the chart that I'm going to give you. Don't worry about it too much for right now. All right, guys. So there is the VSEPR theory, the molecular theory. There is a lot to memorize, but honestly, it's not that hard. You just need to practice with it, look at it, make sure if you're not in class, that you download the cheat sheets that I've included with this to help you memorize those. If you have any questions, guys, let me know, and we'll go from there. Thank you very much. Talk to you later. Bye.